In this video, I will show you how to calculate the potential if you have the quantity that we define as polarization. And by polarization, this is the uppercase P. This is defined as the dipole moment per unit volume. Now, the potential at some observation location, so let's say I have, here is my origin, and I have my object somewhere here. From here to the observation location, this will be my R obs, and this point marked with X, this is my observation location. This is where I want to find the potential and the electric field. Now remember, if you find the potential, if you have the potential V, you can take minus the gradient of the potential and that will give you the electric field. Remember, the electric field has some redundancy in the information that it contains, and this means once you find the potential at your point, at your location, you can also find the electric field. So I'm going to talk about the potential here. If this over here is my insulator, then the potential at the observation location is a sum of two integrals. One will be a surface integral and one will be a volume integral. Okay, the first one is 1 over 4 pi epsilon naught, the constant, a closed surface integral of a surface charge density sigma sub b over r, and I want to remind you what is r. You may have already guessed. By r, I have r obs minus r source. Okay, whenever in my videos you see the vector r, this is the relative position vector from the source to the observation location, over dA, a small an infinitely small surface area. Now, this surface charge density can be found from polarization. This surface charge density is defined as polarization dot product with the vector that is perpendicular to your area at that point. In other words, the dA, your dA vector, needs to point in the same direction as n hat. N hat is the unit vector. Another way, I could have written it as dA hat. Okay, it's the unit area vector. It's the unit vector that is perpendicular to the surface. So if you take polarization, your polarization vector, and you calculate the dot product with the vector perpendicular to your area at that point, that will give you the surface charge density that you need for your surface integral. And the second integral is a volume integral. The constant 1 over 4 pi epsilon naught, the integral over dV, so this is a volume integral, with a charge density, okay, that is defined as minus the dot product between the del operator and polarization. So again, if you have polarization, you can calculate this volume charge density, and then do the integral. The sum of the two will give you the potential at your observation location. So the process, okay, this is the process that you can use when you have these kind of problems. So we will start. If you have the concept of polarization, if you have that quantity, that vector quantity, then in your next step, you will find the surface charge density and the volume charge density. Okay, sigma b, rho b. These are the two quantities here. They are defined with these two equations. Once you find these, then your next step will be to do the surface integral. So let's do sigma b over r dA, and also you will need to calculate the other integral, rho b over r dV. And then when you have those two, you can add them together to find the potential at the observation location. This is the process that you will use in these problems. It is, one more note before I finish with this video. Yes, we do have, let's say, a polarizable object, an object that is polarized. Now, this is one way to think about calculating the potential at some location away from your polarized object. These are these two charge densities, the surface and the volume. We call these the bound charges, and you can derive those two from the concept of polarization.